Hello everyone, how are you today? Good. How was your long weekend? What did you do? Anything interesting? How about you? What did you do during the long weekend? Test. What kind of test? Okay. So that's like national test or regional test or what kind of test? Of course test. Okay. So what course? Programming. Okay. So what kind of test do you have in programming? It's like offline test for like 20 different questions, 7 questions, and you can bring it home and finish, or it's an online test over there. Okay. So how did you do? Back. Okay. So normally, how many questions in average everyone can solve? One, really? So it's a very difficult task. 1, 2, 3. Okay. So if you can solve above like 4, it means you're good. Or super smart. Uh, who is the instructor of programming courses? Oh, I see, I see. Okay, okay. That totally makes sense. Okay, we just mentioned a recursive definition for different structures, such as set or functions. So we have seen how we apply different properties to strings by this different recursive definition, for example, concatenation. So today we will continue this topic to see how we can calculate the length of a string based on this recursive definition. Let's see this example. We have a recursive definition of LW. Okay, actually, this function helps us to calculate the length of the string W. So let's see, what is the recursive definition? So for the basic step, we can define L of lambda. This is empty string. The length of empty string is 0. Okay. And then for the recursive step, we can calculate L of Wx. So remember, W is the string and X is the alphabet. So we can see W in the set is 1 star and X in the alphabet set. So that means you can separate one alphabet from the string to make the string Wx. Then we can define the length equals to L of W plus 1, because we know the length of one alphabet X we can separate the others using the recursive definition L of W. Alright? Now I want you to calculate the length based on this recursive definition. What is the length of the string love? Okay. You need to apply this recursive definition one by one in each step to calculate the length of the string love. So please write down all your process for all your steps. Take one paper. Hello? Take one paper for. Right? Have you finished your answer? One extra point if you share your answer on Blackboard to everyone. Okay, please. Okay, please. Right. No, you didn't give your final answer. What's the length of this string? You need to give your final answer. How to close this equation? That's right. Okay, okay, that's good. Okay, so let's see. When we have the string love, we can apply this recursive definition to calculate the length because love we can separate to another string LOV and one alphabet. So we have special name W1 and X1 for the string LOV. which is called W1, and the alphabet E for X1. So once we have W1 and X1, we can follow the definition. The length of WX equals LW plus 1. So we can calculate the length of LOV plus 1. And LOV can be further separated to W2X2, which where W2 is LO and X2 is V. So we have the length of LO plus 2. Okay, so now we can separate LO to W3 and H3. Then we have WL plus 3. Okay, so now we have the final step. Let's see how we close this equation. Because for LL, then we can write there is an empty string lambda contact with the alphabet L. So once we consider lambda as the empty string W4 and L is the alphabet X4, then we can write equals length of lambda plus 4. And we know the length of lambda equals 0. So in the end, we can calculate the length of the string love is 4 using this recursive definition. Okay, what's your name? Okay. I remember you had a very good result in your midterm. Okay, next let's see the topic well-formed formula in propositional logic. So let's see the definition. We define a set of well-formed formula in propositional logic involving true, false, and propositional variables. And the operators from the set are using not and or, imply and by condition. So let's see the basic step. If we have true, false, and any propositional variable s, they are the well-formed formula. Okay, so this is the basic step. Because we have this simple component, true, false, and propositional variable, they are all well-formed formula. In a recursive step, if we have two well-formed formula, E and F, then E and F can be calculated or combined using these operators. For example, not E and FE or FE, E and F, T and only F. They are all well-formed formula. Okay, so based on this definition, we can see this example. If in the basic step we know that P, Q, T, F are well-formed formula, okay, because they are propositional variables or true or false. And then in the recursive step, we can construct more well-formed formula because this form of well-formed formula. So we can combine them using operators. For example, P or Q, because P and Q are well-formed formula in basic step. If P then F, okay, so P and F are well-formed formulas, then we can combine with these operators. Okay, and then we can apply recursive step to step 1 again, because we know in step 1 we have this term, well-formed formula. So if we apply recursive step again, we can write, if we consider this is F, then if E then F is also a well-formed formula, therefore we have if E or Q, then Q and F. So based on this, you can see we can combine or construct or generate new well-formed formulas based on this recursive definition. So actually, what we have learned in chapter 1, you can see all this propositional logic. You can prove that they are well-formed formulas using this definition. Then maybe you can try yourself. Can you construct PQN So actually, this one, and this one, they are not both for formula. Okay, next let's see a new definition for rooted trees. Because we are trying to prove the properties for different structures, such as trees. So let's see the definition of rooted tree. Okay, the set of a rooted tree where a rooted tree consists of a set of vertices containing a distinguished vertex called the root. Okay, and then we have edges connecting to those vertices can be defined recursively by this step. So basically, we have one special node which is called root. Okay, and then we have different edges connecting the root to other nodes or trees. So let's see this definition, how we construct a rooted tree. For the basic step, we have single vertex R as a rooted tree. Because we already have this distinguished vertices. Once we have only one single node, we call this single vertex R is also a rooted tree. And then for recursive step, suppose we have disjoint the rooted tree, T1, T2, to Tn, where is the roots R1, R2, Rn, then we can, starting from a new root R, and then we add agents from R to the root of this disjoint tree, R1, R2, Rn, then it's also a rooted tree. Okay, so let's see. Uh, Basically, this definition tells us for rooted trees, we can have as many subtrees as possible because we can connect to the root to different disjoint subtrees T1, T2, to Tn. Okay, so once you have this root, then you can control the tree. So let's see the process how we construct different rooted tree. For example, for the basic step, we have only one distinguished root R here. Okay. Then for step one, we already have the rooted tree, this one, right? So we can consider this is a rooted tree here. And we have another root R, which adding we can add a new vertex from the root to that rooted tree to form a new rooted tree. And then we can consider maybe we have more subtrees, for example, T1, T2, or T1, T2, 3, T1, T2 to T4. Once we have a new root, we can add edges to the root of that rooted tree to form a new rooted tree. Okay, so if we have four different rooted trees in step one, then we can generate more rooted trees by step two. For example, we can have this one, right? This one is a rooted tree. So this one, okay. And then this one is also a rooted tree, right? So okay. So we have one root vertex R here, and we add edges to the root of T1 and T2. Then we have a new rooted tree here. Okay, so let me give you one example. For example, we have, all right. Please follow the definition of rooted tree to construct this one step by step using this recursive definition. Please write down your step how to construct this rooted tree using the recursive definition of rooted tree. Okay, maybe the first thing you can consider is this is a top-down process or bottom-up process. Do you need to construct a tree from the root and spread to each subtrees to construct the all subtrees? Or we call that top-down approach. And bottom-up approach is you construct the leaf node first and then up back to the root. Do you apply top-down or bottom-up approach? All right. Anyone want to share your answer on Blackboard for 1 point? Okay, please. Wait a second. Uh, please tell everyone how to apply a recursive step for your answer because for recursive step, you need to have rooted trees T1, T2 to Tn, and you have one root connecting the edges to those subtrees. Okay, so what's your answer? Right. No problem, because T1, T2, T3 already rooted the tree in basic step. Okay, so how about step 2? What's your T1, T2, T3 to Tn? You're allowed to modify your answer if you want. That's right. That's correct in step 1. How about your step 2? That's right, because it's correct in step 1. All right. Then go to step 3. I see. Okay. Okay. No problem. Okay, that's right. No problem. I see. Okay, this is good. Okay. Okay, so let's see how he constructs the rooted tree. Because so if I want to name the method, it's a top-down method or bottom-up method. That's right, because you are trying from the root and then construct a subtree by this recursive definition. So let's see what he did. In step one, if we have one root node in basic step, then he constructs three different rooted trees. The root with three nodes, the root with one node, the root with two nodes. Okay, so you know this all is legal, right? Because we are trying to use one vertex and connecting edges to the root to construct a new rooted tree. So these three rooted trees are legal in step one. And then in step two, what it does is, so maybe this one is not necessary. You don't have to run this one. You only need this one, right? Okay, so if we don't need this one, then in step two, he tried to make this root construct from step one, because in step one, we have this rooted tree. And then combined with the rooted tree with one vertex, then we can construct a new rooted tree here. So in step three, he applied the rooted tree in step two, and then two single vertices T1 and T3. Then that makes the whole tree. Okay, so this is the way we construct the rooted tree by the top-down method. So can anyone construct a tree using bottom-up method? Thank you. Very good. Okay, so let's consider this problem by a bottom-up approach. What I'm trying to do from the list. Okay, so the first thing is to consider what is the root of this one. Because if you consider this one is a rooted tree, this one is also a rooted tree, then we can have the root connecting to those trees. So in this case, from the basic step, we have only one single vertex. For step one, we have one root with one node here. Okay, and then we're trying to use this one as the left subtree and right subtree, and connecting the edge from the root. So that will be step two. So for step two, now currently we have this one. And we already know that this node and this node already the rooted tree in basic step. So we can consider these three subtrees using edges connecting to the root node. And that will be our final answer. Okay, so actually you can see you can apply either ways, top down or bottom up, to construct the rooted tree using this recursive definition. All right, next let's see the definition of full binary tree. If the set of full binary tree can be defined recursively using the basic step, a full binary tree has only one single vertex R, In the recursive step, if we have T1 and T2 are disjoint full binary tree, then we can add edges from the root to R, then it will be full binary tree. So actually, if you compare this definition to rooted tree, in this case, we only have two disjoint subtrees, T1 and T2. So maybe you can consider this is a special case for rooted tree because we only have left subtrees and right subtrees. We don't have T1, T2 to the end, only have T1 and T2. So that is a special case for rooted tree. So let's see this process how we build a different full binary tree. For basic step, we have only one vertex R. And then this R is a full binary tree. So it can be used for one and to construct a new full binary tree. So if this one is one, this one is two, then we add H to a new root, which is R here. This will be our new full binary tree. So now we have this one and this one as full binary tree. So we can have this is the left tree, this is the right tree. So we add edges to a new root R. So this is the new full binary tree. So you can choose two of this one, that will be our step one. You can choose two of this one, and that will be this two. Okay, then you can choose one of this one and one of this one. So that will be our tree one and tree two. So in this case, you can apply this step to step 3, 4, 5, 6, and you can have all kinds of full binary tree. All right, next let's see how we apply mathematical induction to this recursive device set. We call this structural induction. So maybe we can see this example first, then we go to the definition of structural induction. Show that the set defined by specifying 3 in the set S, and if we have x and y also in S, then x plus y is in S. So we have seen this problem before, right? So maybe we can go back to where we, oh, yes, it is. We have the subset. In basic set, we have 30. In recursive set, we have x, y, and x. X plus y is also in S. So we can compile the set. Initially 3, okay, and 3 as x, 3 as y. So x plus y is also S. So we have 6 in the set S. Once we have 6, then you can choose 3 as x, 6 as y, and 3 plus 6 is also 9. In this case, you can apply this recursive set again and again to count more numbers in this set. So go back to our question. Actually, this set is the set of all possible integers that are multiples of 3, because we have seen 3, 6, 9, 12, 15. So in the end, all numbers in this set are multiples of 3. So let's see how we prove the properties of this set. Especially this set is defined by recursive definition. All right, so firstly, we can see it's not easy to prove that this set contains all multiples of 3 because we need to apply these rules again and again to generate new numbers. So once the number is not generated yet, we cannot make sure if it is a multiple of 3. Okay, so in the end, we change our ways to prove. We have another set which is A. If A considers all possible integers which are divisible by 3, which also means the set A is the set of all numbers which are multiples of 3. Then we try to prove that the set A equals the set S. Okay. Just like I said, if we want to apply direct proof to the original function, it's not easy because you need to generate a new elements. All new elements are multiples of 3, so it's not easy. So instead, we have another set A, which are all positive integers equals to 3. And we want to prove the set A equals to set S. Right? So remember, we want to prove the set equality. We need to show that A is the subset of S, and S is also a subset of A. Then we can show that they are equal sets. So let's see the definition of if A is a subset of S. So the definition is the element S is A, and the element is also S. Then we can claim that A is a subset of S. So let's see how we prove that A is a subset of S. Okay, so we can have this positional function P of n, which is the statement 3n belongs to S, because A is a set of all possibilities divided by 3. So we can claim that if all elements in A equal element also in S, so all elements in A, we can write the general form of 3n. That means 3n, if we replace n by natural numbers, then it can be divisible by 3. If 3n belongs to S, that means A is the subset of S. Okay, so first thing we want to prove that P of n is true. So let's see how we apply mathematical induction. For basic step, it's easy because it's 3 times 1. When n is 1, our starting point, 3 in S. That's right, because we have the basic definition for this set. 3 is already in S. And then in inductive step, we assume P of k is true. And let's see how we prove that P of k plus 1 is also true. P of k is true. That means 3k in S. We assume this is true. Okay, and then let's see what is P of k plus 1. Okay, actually P of k plus 1 is 3 times k plus 1. It's 3k plus 3. Okay, and now we know we assume 3k in S. And 3 also in S. So if x in S, y in S, then x plus y is also in S. So we can claim 3 times k plus 1 is also in S. Okay, now we prove that P of k is true. So we claim that P of n is true. That is, A is a subset of S. Alright? So let's see the other direction. We need to prove that S is also in A. So how we construct this set S is also can be divisible by 3. Okay, so for basic set, we have 3 in our set S, and 3 is 3 times 1, so it can be divisible by 3. For inductive step, let's see, for our recursive definition, we add x plus y in S, x and y in S. Okay, so in this case, we assume that x and y follow the properties. If x and y also in A, then how to derive that x plus y is also in A? So if x and y in A, that means x and y can be divisible by 3. Okay, so we can write x equals 3 times k, and y equals 3 times p. Then x plus y actually is 3 times the resistance k plus p. Okay, that means x plus y is also divisible by 3. Alright, now we have shown that if we have definition for the set S, and the numbers generated by basic step and recursive step. We can prove all these elements is also divisible by 3. That means if x is a, now we can jump to the conclusion if A is a subset of S and S is a subset of A, actually they are equal set. That means you don't have to verify each element in the set S because we already proved that the set S equals the set A. That means all elements in the set S is divisible by 3. All right, so let me remind you first. Actually, we proved the first part by mathematical deduction because we have seen we have the basic step and we have the inductive hypothesis P of k, and we try to prove that P of k plus 1 is also true. So this is a very standard form of mathematical deduction. For the second part, actually that's what we are going to introduce the structural induction. So let's see the definition. Okay, to prove the property of the elements in a recursive defined set, we use structural induction. Basic step, we need to show that the results holds for all elements specified in basic step. And then for the recursive step, we need to show that if the statement is true for each element used to construct the new elements in the recursive step, then the results holds for these new elements. So let's see this, and we can compare it to our previous question to see better understand the structural induction. So for the basic step, when we apply structural induction, we need to show that the results holds for all elements in the basic step. Okay, so maybe we can go back to our proof. In this proof, we can see 3 in S. Actually, this element is generated by basic step in the recursive definition. So we need to show that the element generated by basic step in the recursive definition also follow the property. It can be divisible by 3. Okay, so that's the first step of structural induction. And for the second step, recursive step, we need to show that the statement is true for each of the elements used to construct the new elements. So in our previous case, we assume if we have xy, use xy to construct x plus y, and x and y, we assume they follow the property. In other words, x and y is divisible by 3. Then we need to show that the new element using this element already also follow the property. So that's how we approve that x plus y also divisible by 3. Okay, so let's see this recursive step again. If each of the elements used to construct the element in the recursive step, then the result holds for new elements. Okay, so x and y, we use x and y to construct the new element x plus y in the recursive step. Then the result holds for new elements. So x plus y is also divisible by 3. But we need to show that it follows the same property for new elements. So that is structural induction. So next, let's see more example of recursive definition because we will use these two definitions to our next question. So this is the definition of height of the full binary tree. Okay, let's see how to define the height of the tree. For basic step, the height of a full binary tree, you have only one root r, and the height of the binary tree is 0. So if we have only one root r, then the height right of the tree is 0. And then for recursive step, if T1 and T2 are binary trees, then we use T1 and T2 as left and right subtrees for the binary tree. Then the height of T is defined by 1 plus max of height of T1 and height of T2. Okay, so maybe we can see this example. So if we consider this tree is T1 and this tree is T2, okay, so we know that what is the height of this tree? We need to choose the max from height of T1 and height of T2. So we know height of T1 is 0 because we only have one single root for T1. And then for T2, what's the height of this one? So we know we have the root here, and we have only one. Okay, so this is not a full binary tree. So maybe we have another subtree here. Okay, so if we have the left tree and right tree with only one vertex, then the height is 0. Okay, so 1 plus max of 0 and 0 is 1. So height of T2 is 1. Okay, now we have the height for this tree. So it's 1 plus max of T1 and T2. Okay, so it will be 1 plus max of 0 and 1. Okay, so the height will be 2. Okay, now you know the height of this one is 0. The height of this one is 1. The height of this one is 2. So maybe you can trace from the root to the leaf to see how many steps you are traveling this tree. That will be the height of this tree. Or you can follow this recursive definition to calculate the height of the full binary tree by yourself. Okay, that's the definition of the height of a full binary tree. Next, let's see the number of vertices n of the full binary tree T. So for basic step, the number of vertices of full binary tree T, if we have only one root vertex R, then the number of the tree is 1. Right? So this is completely correct because when we calculate the number of vertices, once we have only one single root R, then the number of vertices of this tree is 1. Then for the recursive step, if we have T1 and T2 as the left and right subtrees, then the number of vertices of this tree is 1 plus number of T1 and number of T2. Okay, so intuitively this is correct because we have one root and we have the left subtree and right subtrees. So the total number of the vertices will be 1. This is the root number plus the number of the T1 and number of T2. Okay, so once we have these two definitions, next let's see the example how we apply structural induction for what do we have for this definition. Okay, so this is a theorem. If T is a full binary tree, the number of vertices of this tree T is less than or equal to 2 to the power of the height of the tree plus 1 minus 1. Okay, now you can see we have the formal definition n of t and h of t. Okay, we have this recursive definition in our previous slide. Let's see how we construct the structural induction to prove this theorem. All right. Remember, for basic step, we need to prove that the property holds for all elements in the basic step when we have this recursive So let's see. The results holds for full binary tree when we have only one root vertex r. So n of t equals 1 because we know this from the representation of number of vertices once when we have only one vertex r. And height of t is 0. This is also derived from the representation. Now we can calculate if it follows the property or not. N of t is 1 is smaller or equal to 2 to the power of 0 plus 1 minus 1. So this is also 1. So 1 less than or equal to 1. This equation holds for the element defined in the base set. And we have the full binary tree with only one vertex r. Then this property holds. As the recursive step, we have T1 and T2 as our left and right subtrees. Then we assume this property holds for elements used to construct a new elements. So if we have T1 and T2, then we have T1 and T2, the property holds for T1 and T2. Therefore, we can write n of T1 is equal to 2 to the power of h of T1 plus 1 minus 1. And this property also holds for T2. Okay, and then we need to prove that if the property holds for the current elements, then it also holds for the new elements. So let's see, what is our new elements? It's tree T, with T1 and T2 as its right and left subtrees. Okay, so we can apply the recursive condition from n of t. Actually, n of t equals 1 plus number of t1 and number of t2. This is what we have in the recursive condition of the number of vertices. Then we can replace this equation by what we already know for the properties holds for t1 and t2. So if n of t1 is this, then 2 to the power of n h of t1 plus 1 minus 1. Then we can replace these two terms by these two terms. So we can rewrite this equation by this or equal to 1 plus this 1 minus 1. Okay. Now we have 1 minus 1 minus 1. So in the end, we have a minus 1 in the end of this equation. And then we have these two terms add together. Okay. And then we can rewrite this equation by it is less than or equal to max of these two terms. Okay, if we assume one of these terms is larger than the others, then actually we can choose the larger one to form this inequality. The original equation is less than or equal to max of this two. Okay, times 2. Okay. So, and then we can rewrite this equation because when we max these two terms, actually we have the variable ht1 and ht2 here. So we can move the max operation to the power. It will be 2 to the power of max these two terms plus 1. Alright? And then what is max of ht1, ht2 plus 1? Actually, it's the definition of the height of the tree, right? So we have the height of the tree is 1 plus max of the height of T1 and T2. So here we have max of height of T1 and T2 plus 1. Okay, so that we can follow the recursive definition to write 2 to the power of h of t minus 1. Okay, then we move the 2 to the power, then it will be 2 to the power of h of t. plus 1 minus 1. That will be our theorem. Okay, so basically you can see the structural induction is closely combined with the recursive definition. We almost use every recursive definition in our steps. And then you need to remember, when we apply structural induction, actually we are trying to prove that the new elements also has that property. For example, we assume that T1, T2 follows the property of material. Then we prove that a new four-dimensional P, A of T, also follow that property. Assume T1, T2 already follow that property. Okay, so this is the structural induction. All right, let's see if you have any questions so far. 有听懂吗？还可以吗？好，可以的话我们就继续喽。好。All right, let's jump to our last topic, generalized induction. So we usually use generalized induction to prove results about set other than integers. That means we don't prove the properties for integers. Instead, we prove the property of set of other elements. That element has the well ordering property. Okay, so let's see what is well ordering property. We have the order pair, which is constructed by numbers. So let's see how we specify the order of the order pair using integers. For example, we have 1, 8, and we have also integer pairs, order pairs, 3, 2, 3. Okay, so can you define the order? Which one goes first? Because we know 1 is smaller than 2, but 8 is larger than 3. So we know the order for integers 1, 2, 3, 4. This is okay, but once we have the order pair 1, 8, and 2, 3, how to define the order for these two pairs? Okay, now we can have lexicographic ordering. Okay, it tells us if we have x1, y1, and x2, y2, these are two order pairs with the n times n. So we choose these integers, okay, from natural numbers. Then we can define its order. If x1 is greater than x2, then x1, y1 is greater than x2, y2. We only compare the first element. If first element is 1, this then is 2, then x1, y1, this pair is basically the pair x2, y2. Okay, we have the second condition. If x1 equals x2, then we compare y1 and y2. If y1 is less than y2, then the pair x1, y1 comes, which is less than or equal to x2, y2. We call this graphics ordering. You can also apply this well ordering properties to strings. If you compare its lexical ordering for love, you, how to distinguish the order of the string love and you. We can also apply this lexical graphics ordering. Okay, next, let's see. Let's go back to generalized induction again. We are trying to prove some properties about the set of this, for example, order pairs. Okay, anything other than integers, we can apply generalized induction to prove that this wheel ordering properties. So next, let's see this example. Okay, assume we have A M N defined for the order pair Mn by A00 equals 0 and AMN by the following equations. If n larger than 0, then AMN equals to AN minus 1 plus n. If n equals 0 and n larger than 0, then AMN equals AN minus 1, n plus 1. Okay, so maybe we can try to answer what is A11. Okay, because we already have the order N from natural numbers, and what is the number A11? Okay, so let's see, we have these two conditions. If we have n equals 1 and n equals 1, then if n equals 0, we use the first condition. If n larger than 0, we use the second condition. In this case, n is 1, so we use the second condition. Actually, A11 equals A10 plus 1. Or we use n minus 1. N now is 1. So 1 minus 1 is 0. And n is 1, so we plus 1. Okay, so now we know A11 is A10 plus 1. Next, let's see what is A10. Okay, so by this time, 10 when n is 0, we use the first definition when n is 0, n larger than 0. So now we have n minus 1. So we have n now is 0 plus 1. So this is A10, and we have plus 1 in the end. Okay, so now we go back to the initial definition. A00 is 0. So if this one is 0, so the number is 2. Okay, now we know A11 actually is 2. Okay, so it's not easy to calculate A100. Because when you need to calculate this one, you need to start from the substitution step by step and go back to the initial condition A00. Then you can know what is A199. So here we have the equation or formula for A and N. Actually, you don't have to write each steps. We already have this equation to calculate what is the number N and N. N plus n times n plus 1 divided by 2. So maybe we can verify this equation. So if we use the equation instead of the substitution, so we have A11 equals n is 1, n is 1 times 1 plus 1 divided by 2. So it will be 1 plus 1, it will be 2. Now we know this is the formula for this special number A and N. Okay. Now how to apply generalized inductions to prove that this equation is true. Alright, so let's see how we apply wheel ordering properties. Let's go to basic step A00. If we use n is 0 and n is 0, then we have 0 plus 0 times, here is 0 plus 1. Okay. 0 times 0 plus 1 divided by 2. So in the end is 0. So A00 is 0. follows our initial condition. Next, for the inductive step, assume that A n prime equals n prime plus n prime times n prime plus 1 divided by 2. So now we have n prime. N prime is listed our pair in the next ordering. Therefore, if it's listed in n, then it follows these properties. Okay, so we can calculate n, n prime, n prime. Okay, and then let's verify for this formula, a and n. So now we have two different cases because we don't know if n is 0 or larger than 0. So we consider n is 0. Then by inductive hypothesis, uh, all pair number less than n follows the property. Okay, so if we have the order pair n minus 1, n this one is less than the order pair n. So this one follows the equation. And then we can see a and n. Actually, we use the first equation because we assume n is 0. So the result is a n minus 1 n plus 1. Okay, so now we know this is the order pair n minus 1 and n. So we can apply this equation directly because we assume all order pairs listed in n follow the property we assume are true. So the results will be n minus 1 plus n times n plus 1 divided by 2, n plus 1. Okay, now we can see the results equals n plus n times n plus 1 divided by 2. It's just our equation. Okay, next let's see the second case. Once n is larger than 0, then we need to use the second definition. So we can see actually the order pair n and n minus 1 is also less than n by the definition of next brackets order. Okay, so if the pair n and n minus 1 follows the property, then we can apply this expression again. It would be n plus n minus 1 times n divided by 2 plus n. Okay, so after some simplification, you can see it is also n plus n times n plus 1 divided by 2. Okay, now we have proved that actually this special definition for the number a and n, we can calculate a small formula to derive the n terms. Okay, so we call this generalized induction because we are trying to prove some well-ordering properties other than other integers. All right, for this section, we have the homework assignment 5.1 to 5.3, and you can finish this homework assignment for 2 weeks. All right, any questions for the lecture today? Okay, if no question, see you in Thursday.
自己关掉就好。
对，录影有关吗？好像也没这个。